Assalamu alaikum and hello everyone. In this video I'm going to be solving a question on solution thermodynamics, so let's just get straight into it. In this question we have been provided with data in which we have the mole fraction of A and the integral molar volume of the solution. In part A we've been asked to find the volume change, which is delta V, when 2 moles of A and 3 moles of B are mixed together to form a solution. So the first thing that we should realize is that whenever pure components are mixed together to form a solution, we can only use integral molar properties. We cannot use partial molar properties in that situation because A, we've been not given partial molar properties over here, and B, that partial molar properties can only be used when you're adding a component to a large amount of solution. Over here we're making only a small amount of solution. This can be seen over here as we're adding 2 moles of A and 3 moles of B to form 5 moles of solution, AB solution. Right. So let's write down all of this in form of an equation, as it makes things a lot easier when solving a question. So you have 2 moles of A plus 3 moles of B, which gives you 5 moles of the solution. Right? So instead of writing down AB over here, I recommend writing down the mole fractions, as it makes things a lot easier. To find XA, which is the mole fraction of A, simply divide the number of moles of A by the total number of moles, which gives you 2 divided by 5, which is 0.4. Similarly, you can find the mole fraction of B, which is NB divided by N, which is 3 divided by 5, and it gives you 0.6. So let's just write them down over here. 0.4A plus 0.6 B. All right. Now, the question asks us to find delta V, which is volume change. So volume change is nothing but the final volume minus the initial volume, just like any other change. So the final volume is actually the integral molar volume of the final solution over here. So that's going to be just V. Minus the initial volume is nothing but the sum of the pure components volume. So that's going to be NA multiplied by VA naught plus NB VB naught. So now we have to find out VA naught and VB naught. So to find V, we just simply go to our equation over here and we see that we have 0.4 moles as the mole fraction of A. So we go to our table at 0.4, we can see that we have 13.2 as the integral molar volume. So we just simply write that down over here. To find out the pure component A volume, we just simply look at when the mole fraction of A equals to 1 or the mole fraction of B equals to 0, as it's a binary system. And from the table we can see that it comes out to be 12 cm cubed per mole. Similarly, we can find VB naught, which is when the mole fraction of B equals to 1 or the mole fraction of A equals to 0, and this comes out to be 10 cm cubed per mole, as we can see from the table over here. Alright, so now we just simply plug in these values over here into the equation, 13.2. Now, as it's in moles, cm cubed per mole, we just simply multiply it by the number of moles of the final solution, which is 5, minus, now, 12 multiplied by 2, plus 10 multiplied by 3. And from here we get 66, and all of this gives us 54. And this gives us 12 cm cubed per mole per 12 cm cubed, which is the volume change of this solution, and this is the answer for this part. Now, in part B, we've been asked to find the volume change, which is delta V, when 1 mole of A is added to 4 moles of solution with the initial composition of the solution as 0.5. So in this part, again, we should realize that we have to use integral molar properties because we're adding a component to a small amount of solution. 1 mole of A is added to 4 moles of solution, AB solution. Now in this solution, we can see that we have the mole fraction of A as 0.5. So this is, again, the mole fraction of B is also equals to 0.5. And from here, we can deduce that the number of moles of A is actually 4 multiplied by 0.5, which gives us 2, and which is the same for B as well, 2 moles. All right, so this, when 1 mole of A is added, we get basically 5 moles of solution of AB, right? So over here, we have a new mole fraction, and we're going to have, obviously, new mole fraction of A and B both. All right, so to find basically X A prime, we have to realize that we initially had 2 moles of A, and now we've added 1 more mole, so it's going to be plus 1 divided by the total number of moles of the solution, which is 5. So it's going to be divided by 5, and this gives us 0.6. Similarly, we can find XB prime, which is going to be 2 divided by 5, which gives us 0.4. So we can write them down over here. This is 0.6, and this is 0.4. All right, now let's write down our equation, which is going to be A plus 4 moles of the solution, 0.5A plus 0.5B, and this is going to give us 5 moles of solution, in which we have 0.6A plus 0.4B. Right. So to find out delta V of this solution, we're going to use an alternate path. We cannot find it directly. So we're going to go from here to 2A plus 2B plus A, and this is going to go over here. Just like how we do it in Hess law, we're going to use an alternate path over here. All right. So delta V is going to be nothing but the sum of delta V1 and delta V2. All right, so to find delta V1, we need to realize that this is the opposite of the reaction that we did in part A, in which we were going in this direction, but over here we're going in the opposite direction, right? We have the solution and we are going towards the component. So we have to put a minus over here. This is extremely important, or else all your answers will be wrong. So we're going to have V prime, which is the volume of the solution, minus the initial volume, which is going to be NA VA naught plus NB VB naught, just like we did in part A. So over here we can see that we have 0.5 as the composition of A. So we can see from here that if we go to 0.5, we have 13.5 as the integral molar volume. So we can just simply write it down, 13.5 times, we have 4 as the total number of moles of the solution. So we can multiply it by that, minus 2 times, as we calculated in part 1, it's going to be 12 over here, plus 10 times 2, and this gives us minus 54 plus 44, and this gives us minus 10 cm cube. Now we have to find delta V2, which is going to be simply V double prime, which is going to be a different integral volume, minus the pure components volume, which is going to be Na plus 1, because we've added our 1 mole of A in the solution, VA naught, plus NB VB naught. Now we can see from the equation over here that we have in the final volume, we have 0.6 as the mole fraction of A. So we can simply go to our table, and we can, from here we can see that the integral molar volume is 13.6 multiplied by 5, as it is the total number of moles of the final solution. Now minus 3, as it's the number of moles of the final solution, as we have, right, as we saw over here, plus multiplied by our pure component volume, plus 2 multiplied by 10. This gives us 68, minus all of this gives us 56, and this comes out to be 12 cm cube. Now, the question actually asked us to find delta V, so which is, as we said before, it is delta V1 plus delta V2. So this is going to be 12, it's going to be minus 10 plus 12, and this comes out to be 2 cm cube. And there you go. This is the volume change of this of this of the solution and the answer for this question as well. Thank you so much for watching this video. Do like and comment on it and subscribe to my channel for more such content.